The last speaker is Tanumoy Mandal, faculty from ISER Trivandrum. He will talk about vector-like quarks. I must mention he is former PhD student of IMSc.
Good afternoon, everybody, and thank you, Sanatan, for introducing me. And also, I would like to thank the organizer for inviting me for this occasion of 60-year celebration. And as he already mentioned, I was ex-student of IMSc. So I was here during this 2007 to 2013. I was an integrated PhD student here. And this is like after almost 8 years, I'm again here, and it makes me sort of nostalgic being here. So, but since time is short, let me start with the talk. So, today the topic of my talk is Mind the Gap, unconventional searches for vector-like quarks. So, there is one reason why I choose this topic, vector-like quarks, because that was my PhD topic, this vector-like quark, phenomenology of vector-like quark in context of LHC experiment. And after finishing PhD, I did not work on this. Only recently, last year, I again started working on this vector-like quark. In that sense, it is also current area of my research and interest. Okay, so these are the papers we had this last year on this vector-like quark, and my talk will be based on these 3 papers that we had recently. So this is brief outline of today's talk. First, I will tell you brief idea of vector-like quark searches and current limits and possible gap areas in the vector-like quark searches. And then I will tell you about the roadmap of interesting signatures and benchmarking at the LHC, and also future prospect of searching these vector-like quarks. Okay, first of all, what is vector-like quark? So they are, of course, hypothetical particles and spin-half particles, and they are colored particle and kind of heavy companions of the standard model quarks, you can say. And why they are called vector-like? Because in standard model, all the quarks or all the fermions are chiral, because they are left-handed component and the right-handed component, they transform differently under the gauge group. On the other hand, these vector-like quarks, they are special, so they are left-handed and right-handed, both components transform similarly under the gauge group. So they can have different representation. For example, they can transform as singlet or doublet or triplet under the SU2 gauge group of the standard model, which is the weak part of the standard model. And another thing, why first of all we would like to search them? They are kind of omnipresent, they appear everywhere in almost all theories around this TeV scale. And therefore, searching them, if you really find them in collider experiment, so that will be direct, clear-cut hint of new physics beyond the standard model. So that is why this program of searching vector-like quark in collider experiment is very actively going on at the LHC. But unfortunately, nothing has been found yet. And what does it mean? So that means that either these masses of these particles are very heavy beyond the reach of the collider, or so far we have considered certain search channel to search for these particles. Maybe the vector-like quark is not dominantly decaying to those search channel. Maybe it is decaying to something else. So therefore, since we have not considered those in collider experiment, we might have missed it. They are still like within that collider reach, but we might have missed it because we have not considered those channels. So that is the motivation of this talk. So we consider some non-standard decay modes of vector-like quark. Okay, so what are the non-standard decay modes? So for example, in the existing search, this Atlas and CMS collaboration, they have considered only single particle extension of the standard model. So standard model of particle physics is there. So in the particle spectrum, they have added by hand a vector-like quark. And that is the minimal approach. That is like Occam-Razor principle. You start with minimal approach and then you try to search for these signatures. Now since nothing has been found, so minimal approach may not work. So what we have done, we have added one more particle along with that vector-like quark. So one more scalar we have added here, and this vector-like quark can decay to standard model quark and this new scalar phi. So that is the new interaction in the non-minimal setup we have added here. And of course, it is not just by hand addition. So it is kind of bottom-up approach that we are considering, but there are of course top-down approaches or motivation where this vector-like quark and this scalar, they are present together. And then that motivates this particular decay modes. Okay. Now how, so you can get the interaction of this vector-like quark and with the different particles. So the formalism that I am showing, don't worry about all these equations, but the basic idea is that this capital T is our vector-like quark and the small t is our standard model quark or the top quark. So this vector-like quark will mix with that standard model quark, and through the mixing, it will have different decay modes. So for example, if the vector-like quark mixes with this top quark, third generation quark, it will decay to bottom and W boson and Z top and Higgs top. So these three decay modes are there, and one important feature of that vector-like quark is that it will have flavor changing decay, which is missing for the chiral quarks that is present in the standard model. Standard model quark, they are chiral. For chiral, tree level flavor changing decay are not there. So that is one unique signature of vector-like quark. Let's move on. So this is like how you diagonalize that mass matrix in the previous slide I showed, and you can get the eigenvalues of this matrix, and they are nothing but the masses of that standard model quark and that new particle companion. And you get the necessary interactions for your further calculations, like interactions with Higgs boson, interactions with W and Z boson. And here, since that new scalar I have added, so two more couplings we have added here, lambda A and lambda B, shown in red. So these are the existing LHC searches, in the sense that this vector-like quark, if it is in singlet representation or doublet representation, they will have specific proportion of their branching ratios. Like for example here, this T, if it is in singlet representation, it can decay to this WV mode with 50% probability. And that ZT and Higgs T, these two modes, 25 each. So total like 100%, 50, 25, 25. Now with this just single particle extension, if it is like singlet vector-like quark from the pair production, the current limit is about 1.3 tera electron volt. And if you have like assumption that it is decaying exclusively to that ZT mode, 100% branching ratio, then the limit is highest, 1.6 tera electron volt. So limit is quite high. Now here, since we have two particles, so first thing we should consider their branching ratios or the decay modes that it can decay to. So these three lines you can see here, these are the standard or conventional decay mode that so far people have considered. Now we have added this new decay mode and this mode, yellow line here, and you see the corresponding probability is very high, almost close to 1. Of course, that will depend on that parameter choice. So the point is that there is a large parameter space where you can realize this new decay mode to be quite high. So that is very important. Now the second thing is that once it is decaying to top and this new scalar phi is also unstable particle and it will eventually decay. and what it will decay to. So there are possibilities here shown in this 4 lines. Now phi will have loop induced decay, which is generally suppressed, and phi can also decay to Tt bar. So maybe it is. So here in that pink line, you can say that Tt bar is tree level decay. Now that common consensus is that usually loop induced decay is much suppressed compared to tree level decay. But here in this parameter space, what we have found that indeed that loop induced decay, which is that gluon mode, is much higher compared to that tree level decay to Tt bar, above the Tt bar threshold. And you might think that this parameter space is very much fine tuned, which is not. What we have seen that indeed there is a large parameter space where that loop level decay is dominates over the tree level decay. So then the main point is here that once that T prime or that capital T vector like quark is produced, it will decay to that new mode, and this scalar will eventually decay to 2 gluons. So we considered these things, this channel, and then we used some sophisticated techniques to find the sensitivity of this particular channel. Now here, this is the rescaled mass limit. Because we are introducing new channel in the setup, all the existing limits that is no longer applicable, or you have to modify that limit. So for example, if the corresponding branching for this new mode is say 50%, then the mass limit is 1.3 TeV. And if this channel is not at all present, then the mass limit is 1.4. So essentially the mass limit will reduce if I introduce new mode into my setup. And that is another limit you can get from direct production of that new scalar phi through gluon fusion. So these are the limits that you should consider when you are trying to get the parameter space. So what we did, we considered those limits and made a parameter scan on the free parameter of our theory. And what we found here is that indeed, as I said before, there is large region of parameter space shown in this colored region, red or blue here, that is open for this new particular channel that I mentioned. Okay, in one paper, that roadmap paper, we listed various possibilities of different channel or the final state that one can consider. Now you see, this is a very big list. Only handful of them are considered in these references, but there is lot of channels that is left open. So that is indeed a like good direction. One should consider these channels and find out the sensitivity in that collider experiment. Now of course, not all channels are equally good. Some are very good, and you have to pick up the best one for your first analysis. So in the next paper, what we did, we picked up the best channel in terms of the sensitivity of the collider reach, and we found that this channel, this particular channel is very good, and you can probe a lot of like wide region of the parameter space using this channel, where the conventional or the standard channel will not work. So standard channel cannot probe that parameter space. You have to use this particular channel to probe that region of the parameter space. So I am not going into the details of that analysis, where we have used machine learning technique, which is like very advanced technique people are nowadays using everywhere. So we also use that machine learning technique to satisfactorily isolate that background, huge background, and then we isolated the signal, and we obtained very good sensitivity, which you can see here. So since we have two mass parameters here, one is that vector like quark mass and that scalar mass, so it is essentially two-dimensional plot. And in particle physics, we use this thumb rule. If you exceed that 5 sigma confidence, then you say it is discovery. So you see 5 sigma is somewhere here. So you get essentially some contour here that will give you that 5 sigma discovery contour. And you can see these contours here in this 2-dimensional plot. Okay. Now, so far I discussed the top partners, the companion of that top quark, heavy companion of the top quark. Now, similarly, bottom quark can have also its heavy companion, which is known as this vector like B, denoted by that capital B here. Now, if I want to use that same technique that I have used for that vector like top search, that will not work. Same technique means same final state or similar final state. Why? Because you see this vector like bottom will decay to bottom quark and then new scalar, and that new scalar will decay to gluon gluon. So essentially you have B like bottom quark gluon gluon and anti-bottom and gluon gluon, this kind of final state. So all are hadronic. The Large Hadron Collider, that machine is basically PP collider, where you have like total mesh. So if you have all hadronic final state, you cannot isolate this particular signal. So what we did, we considered some kind of asymmetric final state. So where the one vector like B is decaying to this mode, the other one is decaying to conventional mode. So it is kind of interplay between that conventional and unconventional modes. And that was also very challenging in terms of background reduction, and we took that challenge and finally we obtained at least some amount of sensitivity, particularly for this channel. And you can see this sensitivity plot here, where you can reach that 5 sigma confidence, and that region you can discover in the future experiment. Okay, so this is the final plot where you can, like the region of the parameter space that you can probe with that 5 sigma confidence limit. And if within this parameter space nothing has been found in future, then at most what you can do, you can exclude the parameter space if nothing has been found. And the thumb rule that we use for exclusion is the 2 sigma confidence limit. Of course, that region should be bigger than the 5 sigma, because you can exclude more than the region you can discover. So this is the region you can discover in that future LHC experiment, and this is the region that you can exclude in this future LHC experiment. Okay, so as I discussed already, that we have introduced new channel which you can use to search for this vector like quark. And here we have introduced, of course, non-minimal model, where one quark is there, new quark is there, and addition to that you have another scalar. And this kind of models are like common in many like top-down approaches like composite Higgs model or extra dimensional model. So if something is found in this particular channel, that will also tell us more about the fundamental theories. So that is another good thing. If you really find this particular channel, then it can tell us more about the fundamental theory. And another important point that I already mentioned, that common consensus is that loop induced decay of phi is generally suppressed over the tree level decay of phi. But here we found that large region of parameter space is open for that new channel, where you have this loop induced decay much more bigger than the tree level decay. And using this pair production channel, we found that sensitivity, but I showed that big table where there are a lot of options available, like pair production, single production, many possibilities are there. So these are like all are very important. Kind of it can act as kind of complementary search to that existing thing. So here I end my talk. So thank you for your attention.
Thank you, Tanmay.